In this video, we're going to talk about operations on radicals. We're going to kind of cycle through adding, subtracting, multiplying, and dividing, and what that looks like with a square root or a cube root. We'll start with adding and subtracting. If I want to add two square root or cube root expressions together, I'm going to combine like radicals. In order for the radicals to be alike, they have to have the same index, which means they're both the same type of radical, both square roots or both cube roots, etc. And they have to have the same argument. The argument would be what's inside the radical. For example, here, the argument would be a 5. Okay, so we'll try this example first. Think of this as saying, like, I have 3 square roots of 5. Right? If you think of the square root of 5 like an object, right? Like a coin. I have 3 of those coins, right? And I also, in a separate stack, I have 4 of those same coins. So if I put them all in one stack, right, I don't need to worry about the value of the coin right now. I'm just counting how many I have. So I have 3 plus 4. I have 7 square roots of 5. That's the basic idea here. Okay, and it works the same way with subtraction. Both of these are square roots. More specifically, they're both square roots of x, so I can subtract 2 of them, take away 7 of them. I'll have negative 5 square roots of x. Okay, what if they are not alike? Would be a good logical question to ask next. Sometimes we need to simplify first, and when we do that, we kind of uncover the fact that they are alike, and then we're able to add or subtract them together. So let's try that out. So if I have the square root of 125 plus the square root of 45, I cannot combine these the way they are right now. They are both square roots, but they don't have the same argument. And so I need to try and bring some things to the outside using the lesson we just learned about simplifying radicals to be able to, maybe they're alike and then I can combine them. I want to break up 125 into 2 things that are multiplied, and one of them being a perfect square. I know 125 is 25 times 5. So I'm going to use the product rule to break that up. The square root of 25 is going to give me 5 times the square root of 5. I want to do the same thing with 45. 45 is 9 times 5. And 9 is a perfect square. So the square root of 9 is going to give me 3 times the square root of 5. Now that I've simplified them, now they're alike. They're both the square roots of 5, just like the example above, so I can count up how many square roots of 5 I have. 5 plus 3 would give me 8 square roots of 5. Okay, let's add in some variables just for fun. All right, so like we've said in the past, anything that's on the outside, when I bring more things out, all of it gets multiplied together. Okay, so let's do that. Let's leave the 10a kind of on its own just to hang out for the moment on the outside. What if I'm taking the square root of 4a cubed? What can come to the outside? Square root of 4 is going to give me a 2. I have 3 a's. I can make one pair, so 1a can come out, the square root of a squared, if you will, and then I'll have 1a left over inside. Okay, same thing for this second piece. Let's leave the 3 there to hang out. For the square root of 9a to the 5th, what can come to the outside? I can take the square root of 9. It's going to give me a 3. If I take the square root of a to the 5th, how many a's can come out? For a square root, it's going to take one of 2 equal factors. So I can make 2 pairs out of 5. So that means 2 a's are going to come out. That accounts for 4 of them, but I have 1 left over without a pair, so that one stays inside. Okay, this looks a little bit messy because we want to multiply all the things that are out front, so let's do that now. So this becomes 20a squared times the square root of a minus 9a squared times the square root of a. Okay, and I did put in a side note down here at the bottom. So when we are combining with radicals, we do need the radicals to be the same. If variables are involved, we also need them to be like terms, which means that we need the variables on the outside to match as well. Since I have an a squared out front and an a squared out front, I'm okay. I can combine these. If the variables on the outside of the square root were not the same, I would kind of be stuck. I wouldn't be able to combine them as easily. But for this example, I can. So 20 minus 9 would leave me with 11 a squared square root of a. Okay, let's look at multiplying radicals. Here is the product rule one more time. Right? I'm allowed to either combine radicals or split them up over multiplication. So if I'm multiplying 2 cube roots, let's say, as long as they're the same, I can multiply them. So the cube root of 9 times the cube root of 3 becomes the cube root of 9 times 3, which is 27. For this problem, that's very convenient because 27 is a perfect cube. 3 times 3 times 3, so I'll get a 3 as my final answer. Okay, we may need to multiply things that are a little bit more complicated than that, so we can also make use of the distributive property and FOIL, all things that we've used in previous sections. Okay, it is important to know that when you're multiplying, anything inside a square root can be combined using the product rule. Anything outside the square root is going to be separate from what is inside the square root. So when I multiply the square root of 3 times 4, because the 4 is not inside a square root, it's going to go on the outside, in the front usually. But since the 5 is inside the square root, I'm going to go ahead and use the product rule to combine them and make this into the square root of 15. Okay, we can also use FOIL to multiply with radicals. So as tempting as it is, we know that we cannot distribute the square to each part. We have to use FOIL to do that. So we would want to draw out 2 copies of the square root of 5 plus the square root of 8. So if I use FOIL, the square root of 5 times the square root of 5 would be the square root of 25. Yes, that is definitely going to turn out to be 5, and you could go straight to that if that's easier for you. On the outside, I'm going to have 5 times 8 gives me the square root of 40. On the inside, 8 times 5 also gives me the square root of 40. And then 8 times 8 gives me the square root of 64. So we said this was 5, and we know this is going to be 8. For the square root of 40, what can come to the outside? Remember 40, I can break up as 4 times 10. And 4 is a perfect square, so when I take the square root, a 2 comes out. And that happens for both of these. Okay, for my final answer, I really want to pull in the addition skills we looked at the very beginning. So any numbers right without a square root, I can combine those, and then any square roots that are alike, I can combine those. So my final answer is going to be 5 plus 8 gives me 13, and then 2 plus 2 here gives me 4 square roots of 10. All right. So I do want to talk a little bit about dividing. It's a little bit different than the other operations. So we'll start with what we need to do if we have a square root in the denominator. In a previous video, we said the convention is to, when we make a radical expression as simple as possible, we usually do not have a square root or any kind of root in the bottom. So we need to do what's called rationalizing the denominator, which just means that we're not changing the value of the fraction, we just want to rewrite the fraction in a different way without the square root in the bottom. So to do that, usually we multiply the numerator and the denominator by the same amount. Your book, I think, calls it a well-chosen 1. This would be like 2 over 2, or for us in the next example, we're going to do square root of 5 over square root of 5, okay, something like that, where if I were to divide these, I would get 1. And so I can multiply anything by 1 and not change its value. I'm just rewriting it in a different way. So that's what we're going to do here. Okay, if I have a square root, what I'm really trying to do is get a square root of a perfect square in the denominator so that the radical or the square root goes away and I just get a regular number. So for a square root, remember I need one of 2 equal factors. So I have one factor, I need another factor that looks like it, so that when I multiply across, I'll have 3 square root of 5 on the top and the square root of 25 on the bottom, which I can take the square root of because now it's a perfect square. That was kind of my whole reason for doing this, right? And so I get something that is equal to the original value but does not have the square root on the bottom. Okay, so for a square root, I can kind of mimic what I see in the denominator and use the same thing. And that's because for a square root, I need 2, right? I need a pair. For a cube root, it's not exactly like that. I need a group of 3, right? And so it could look different for a cube root. Same idea, I want to choose a well-chosen 1, right? Something that is going to help me get a perfect cube when I multiply the 2 denominators. Right now I only have 1 x, and to get a perfect cube, I really need 3 x's, so I have a group of 3. So I have 1, I need 2 more. So I'm going to multiply by the cube root of x squared. I have 1, I'm going to add, not add, but I'm going to multiply by an additional 2 x's so that I have my group of 3. In order to be that well-chosen 1, I need to multiply the top and the bottom by the same thing. And then I'm going to multiply across. X times x squared will give me x cubed. the cube root of x cubed, just like we've got it drawn out here, right? That's one group of 3, or I'm going to divide the exponent by 3 because of the cube root, and I'm going to get x in the denominator, and I'm going to keep my numerator. Okay, so really, when we are working with square roots and cube roots, division really looks like rationalizing the denominator. Okay, so the way we divide is by doing what we just did with something called a conjugate. A conjugate is something that differs only by the sign in between the terms. In this section, because we're talking about square roots and radicals, right, one of the pieces will have a radical and the other will not, usually. So actually, I guess that doesn't have to be the case. I'm confusing myself now. I'm not sure. All right, but irregardless, we're going to change the sign, right? If I'm starting with a plus, I'm going to change it to a minus, and that becomes its conjugate. They're like a pair. Okay, and the reason why they're a pair is because when I multiply them, I FOIL them out, I get an interesting result. So let's check it out. Let's multiply these and see what we get. So 1 times 1. On the outside, I'm going to have a minus square root of 3. On the inside, I'm going to have a plus square root of 3. And then the last times the last would be minus square root of 9. Negative square root of 3 and positive square root of 3 add to 0. So I have 1 minus the square root of 9 is 3. 1 minus 3 is negative 2. So what happens is when I multiply two numbers like this that are conjugates, I get a number that is rational, which means I have no radical, no square root, no cube root left. They've gone. Okay, so yeah, I have it already here. The product of two conjugates gives a rational or a real number. This process works for several different types of scenarios. This is just one of them. Okay, so now let's look at the actual dividing. This will be our last example. To divide, remember I said the division doesn't really look like division, it really looks like rationalizing the denominator. So we're going to kind of combine that with the idea of the conjugate. We're going to multiply the numerator and the denominator by the conjugate of the denominator. Okay, so first of all, what is the conjugate of the denominator? Remember we said the sign would be different. So this is 3 plus square root of 7, so the conjugate would be 3 minus the square root of 7. And this becomes our well-chosen 1, right? It's equal on the top and the bottom. So I'm not really changing the value of this fraction, I'm just changing what it looks like. Okay, I'm going to feel more comfortable with some parentheses in here, so I'm going to go ahead and put those in. In the numerator, we're going to be using the distributive property. So 2 times 3. And we only use a distributive property if we have a plus or a minus, and so that's why we're doing it here. Minus 2 times the square root of 7. In the bottom, we're going to FOIL these two together, just like we just did. So first, 3 times 3. Outside would be minus 3 square root of 7. Inside would be plus 3 square root of 7. And then the last times the last would be minus the square root of 49. These two middle terms add to 0 and drop out. So we have 6 minus 2 square root of 7 over 9 minus the square root of 49 is 7. So really that's going to give us 6 minus 2 square root of 7 over 2. And when we divide by a single number, if I have a plus or a minus, I have to divide both parts. So 6 divided by 2 gives me 3. 2 times the square root of 7 divided by 2, the 2's cancel, and I just get the square root of 7. All right, well, I hope that gave you a good idea of how to work with radicals. We did addition, subtraction, multiplication, and then this rationalizing the denominator, which sort of counts as division. All right, I hope you'll take a few minutes to practice some of these ideas. Good luck. We'll see you in the next video.